All right, so in this video and the next video, and so in the next two lectures, we're going to be just going over examples of applying work energy to rigid bodies in planar motion. So we have the luxury of slowing down a little bit in that we have two lectures devoted to example problems here, but they'll be needed because these can get involved, right? And we got to get comfortable with doing this because they can be combined with some of the other analysis techniques that we use. So the last time we talked about how we need to modify our particle work energy principles to be applied to rigid bodies, and we will see that in the examples coming up. But I just want to go over the general procedure, the general recommended procedure, and all of these should play a part in here. This is now for applying work energy principles, work energy analysis to rigid bodies in planar motion. And we always start with a free body diagram, and the idea with this is we identify the forces that are non-conservative and moments that then need to be included that aren't so obvious to be included in terms of the potential energy and kinetic energy. We then write out the energy equation, well, we'll see that. I was just going to write it right here, but we're going to see it in the upcoming examples. Expand and reduce that energy equation, apply kinematics if we need to, and then solve for the unknowns. Okay, so that'll be the general procedure. At least in the beginning here, I'll try to actually write down 1, 2, 3, 4, 5 as we work through problems. And as you go along, you might be able to see where we're going without actually labeling them 1, 2, 3, 4, 5. But my recommendation is follow this straight out. And again, you can do like kinematics before energy equation. But hey, if you do it first, right, might as well just write number 4 and making sure you're like achieving all the different steps. And yeah, it's a nice systematic way to approach problems. Okay, let's get into the first one. Good system here, right? You have to be really careful writing it all up. But we're given lots of information. And what we want to do is work through work energy principles here to determine the rotation rate of this disk, all right, that started over here attached to a spring. That spring has a equilibrium distance, an undeformed distance of 1 feet, and it's stretched out to 5 feet. So we got a lot of potential energy in the system there. A lot of potential energy still right here, right? The disk is so heavy, it's not being like pulled off the ground here, but this disk then rolls along the surface, and so we lose some of that potential energy. That goes into kinetic energy. What kind of kinetic energy? Well, we got rolling of the disk, and we've got this translational kinetic energy as well as the disk is moving to the left. Okay. Yeah, so let's actually include that as well. Right? We're looking to find the omega, but we also have the velocity of g, where g is right in the center location, right? And so we're given the moment of inertia, the mass, and the radius of this disk. We are given for the spring, we're given its equilibrium distance and its stiffness parameter. Okay, let's get going here then. Step 0 sometimes is like any geometrical properties. We're given all that information, so no need to go into that. All right, let's start one up here, which is our free body diagram. Okay, first step. And we will just write out the disk, or draw out the disk, sketch it out, and put the forces on it. Okay, what forces could we have? Well, it's got weight, told to us right in the problem statement, what the mass is. Right? We also know it's connected to the spring through a tension force. We'll call it the the force of the spring. Okay, it's also contacting the ground, so there is a normal force there. And then because it's rolling that way, there's a friction force which is actually needed to provide the rolling. Okay, now let's, okay. We'll talk about this friction as we go along and the work it does. But for now, these are all the forces. Okay, and there's G. Okay, so let's do this now. Okay, so let's now, the step 2 is go to the energy equation. Okay, which says, okay, state 1, state 2, clearly written out in our diagram. Kinetic energy at state 1 plus the potential energy at state 1 plus any other work that aren't contributing to the kinetic energy or potential energy terms. That equals the combination of kinetic and potential energies at the final state. Okay, so first step, what can we cancel out here? Well, there's no motion here at the start, right? We're releasing it from rest, released from rest. So both translational and rotational are 0 at the start. Okay, so no motion at state 1. Okay, we're both thinking, have we checked translational motion and rotational? And there's just no motion. But no, we have 2 components in this kinetic energy at 1. Okay, now this other term here, just want to make a comment that we're going to see a lot. So with these rolling disks, okay, remember this point that's in contact, that's the point where the friction is being applied, right? That's the point of application for that force. This point here, right, moves in a pattern like that, right? So the next motion here for this, let's put it in that, not red, we'll put it in blue representing its motion. That point, its dr is straight upward, okay? So there is our dr vector, the change in position of that point where friction is applied, right? And the reason we're being so careful here is the work due to friction in one of these rolling wheel cases, right? So the work is F dotted into dr, so the actual friction vector dotted into dr. And I'll just talk for it, and then I'll just make a quick note, right? These are perpendicular to one another. The motion of the point is upward, friction is that way. So the work done by friction is actually is nothing here. It's 0. The friction does no work. It's just there to give us the rolling motion. Okay? So application point of the friction moves upward only. This is kind of our qualitative description, right? This is quantitative. So our dr vector is just whatever, the dr is, the infinitesimal change, but only in the j-hat direction. That's what's important, right? So our F dotted into dr is, well, F is in the I-hat direction here. We dot that into dr j-hat, and that equals 0 because I dot j, they're perpendicular to one another. Okay, so friction force does no work in this case for a rolling wheel. Okay, so keep this in mind because we see these systems a lot, right? There's a friction force, it does no work. So for our work energy analysis, that's a convenient result. Okay, so that allows us to say this term is also 0. Okay, friction does no work for an ideal rolling wheel. All right, now the rest of the terms we need to expand. Okay, and so that's 3. Let's do it down here. Expand, okay. So potential energy at 1, and also note there's going to be no gravitational potential energy. Let's make that note up here too. That'll be a good place for this space right here. a little note to ourselves, gravitational potential energy change is 0. So we could put it in, or we could just say, well, let's choose our datum level to be right here. Okay. And then it doesn't change its vertical position at all. Okay, and so our potential energy change is due to the spring only. Okay. All right, so when we expand it and we go to that potential energy at 1, all we have to do is write out the spring potential energy, 1/2 k S1 squared. Remember, that's the distance beyond our equilibrium length. So for S1, that's going to be 4 feet. And that's the only potential energy term. Now, the kinetic energy at the final state, because we do have motion there, both has a translational term and a rotational term. Okay, that's kinetic energy, and then potential energy at the final state. We don't use up all that potential energy. In fact, there's quite a bit left because we're still 3 feet in a stretch of our spring. Okay, and then let's see. Before we go and solve this, if we look at this, we know that term, right? This is going to be 4. We know that term, that's 3. K is given to us. What we don't know are Vg and omega, so we need a relationship, one more relationship that combines those two. And so that's going to be a kinematics relationship. Now, from our kinematics analysis, well, let's put in those S values here first, right? So maybe it's more of a description of the spring. This is just 5 minus 1, 4 feet. S2 is then 4 minus 1. We're just subtracting off that total distance from 1, which is our L naught. So 4 minus 1, so 3 feet. Okay, now that relationship, Vg in terms of omega, just notice this is a rolling wheel, and point P down here, let's put the point, this application point, P. Okay, point P is fixed. All right, so we could do that analysis of a rolling wheel from that fixed position there. Regardless, we get to Vg moves with respect to that fixed position at a minus r omega. Okay? This is because point P is fixed, not moving, has no motion. So what we mean by that is Vp equals 0. And we could work through our kinematics that way, but we've done this enough with rolling wheels. This is the result we get for the velocity of the center of mass for a rolling wheel. Okay, so we are now ready to solve. Okay, and we get that this term, 1/2 mvg squared, is 1/2 mr squared omega squared. Okay, so let's see if we can work this, right? So let's put these both, write these both in terms of omega, pull that to the right side, and we'll move everything else to, move these to the left side, and we'll move all the spring potential energy terms to the right-hand side. So it's going to look like this, right? So we have, both of those terms are going to have a 1/2 that has, let's just write it out. 1/2 m, Vg is now r squared omega squared. Okay, this term as we pull it, well, we're not pulling, we're flipping the equation. So this is 1/2 Ig, which is given there, and that is omega squared, and that equals 1/2 k S2 squared minus S1 squared. All right, both of those, right now we can actually go ahead and solve for omega. Omega is going to be, look, every single one of these terms has a 1/2 in it. Okay, so we have a k S2 squared minus S1 squared divided by mass r squared plus Ig square root that. And are there any tricky units in here? I would say the only one is, remember that the mass is not 30. The mass is, to get it into slugs, we need to, oh, and I did write M. This should have been mg there. Okay, so to solve for the mass, we need to divide 30 divided by 32.2 for our acceleration due to gravity. But I think the rest of this we have somewhere, right? So S1 is 4 feet. Oh, and I switched the order of these. All right, because we didn't pull it to the other side. We pulled this one over to here. So this would be S1 squared minus S2 squared, right? And so I was going to say that would be a problem because we'd have a negative quantity because S2 is less than S1, as we lost potential energy. And we're using up the potential energy in the spring, or a little bit of it. So I think we got it in the right form now. Okay. And let me continue checking this. So S1 is 4 feet, S2 3 feet. Make sure units are all right. K is 2 pounds per feet. We're good there. The mass down here should be 30 divided by, so our mass is 30 pound over 32.2 pound per feet squared. Okay, plug that in. And then our radius is 0.75 feet. That's in feet. And then IG is in slugs feet squared. So plug that in. Okay, so those are all good. Plug all those in, we get an omega of 4.037 radian per second. And at this point, you could then go determine what the translational velocity is too, Vg, right? Which is in right down here. And so we'd have all of the motion described here at our final state, or at state 2 at least. Okay, that's it for this example. All right, so in this next example, we have a cylindrical disc rolling down an inclined plane here. Well, it's going to start to roll because it's stationary here when a couple is then applied. A moment is applied here at 10 Newton meter. And the disc then rolls without slipping due to that couple. Okay, so it wasn't rolling down; it's now rolling after the moment is applied. What we'd like to determine is the velocity of the center of the disc, so point g here, and when it's moved 0.4 meters down the way. So let's start marking this up a little bit. So we know that b is 0.4 meters. We're basically going from state 1 to state 2, and if we can, let's see if we can try to reproduce this in state 2. So if that's the angle there would be about the new center of mass. It's probably going to be overlapping pictures here, but maybe that's the angle coming down. I think we could try to draw generally what we're looking at there, right? That would be the new position at state 2. And so a few things to notice right away, right? This center of mass has then dropped with its elevation and gravity here. So it's going to be a good choice to choose a datum level at one of these two places. So let's say let's say y equals 0 here. So y2, the state of y2 is going to be 0. And then this will be y1, which is above it. And we'll have to work through some trig. Right now, just making general observations. Another thing to notice here is, well, if this line is right there, then we've now gone to that line has now rotated a certain angle away. Okay, so there's definitely rotation going on here, right? Okay, this is also 15 degrees. I don't know, just making graphical notes to myself here. So let's then let's get through our procedure, okay? Let's start with number 1. Let's write out a free body diagram. Okay, so this is at any point along the motion. We're on the inclined slope. Okay, here is my circular disc. There is the center of mass. And let's put on all applied, or all forces that are acting on this disk and moments, right? So we have the applied moment, M, it has a weight, mg, because it's making contact. It has a normal force, and then there would also be friction. Okay, I think those are the four, and those both act right there. All right, that's it. Okay, so next step, let's write out our work energy relationship, right? That says kinetic energy 1 plus potential energy 1 plus our other terms, other work that we need to put in there, kinetic energy 2 plus potential energy 2. Okay, anything we can cancel out, anything that we want to make notes generally here before we actually plug in things. Well, it starts initially at rest, right? It's stationary before the torque is applied. So that means there is friction there holding it up. Okay, so this is at rest initially, so in state 1. So we can say that one's definitely going to be 0. So that's both noticing here that the velocity of the center of mass, so this is g, the velocity, the translational velocity is 0 originally, and there's no rotation, right? So there's no omega, because both of those provide kinetic energy, both translational and rotational kinetic energy. Also, we chose our datum here, so this one is 0, right? Datum chosen at y2. And also, maybe good to note, there's no spring involved here, because that would provide a potential energy that we'd have to consider. No spring, so we don't know. Okay, but those other three terms we might need to consider here because, well, there could be friction, but it actually turns out that this friction does no work. Okay, so let's write this one in red because this is important, right? And I mentioned that I'll mention this in other problems, but here friction does no work. Okay, and that's because, right? Let's see, the friction force and the motion of this point, right, is upward. Right, it would actually be directly that way. I don't want to make this diagram any more confusing. Actually, we could do it over here, right? The motion of this contact point here is upward. That would be the change in position of that point. And with friction acting there, those are actually perpendicular to each other. So if friction acts that way, change in position is that way, F dot dr is 0. F dot dr equals 0. Okay, but this isn't 0 because we have a moment there. We have a moment that has nowhere else to go in here, and so we're going to put it into that term. Okay. So let's write out number 3, which is to actually expand, plug everything in, right? So our potential energy at 1, okay, there's no spring, but we have an increase in our, well, it's height there, plus the moment times theta, right? That is the work due to an applied moment that we derived last time that we need to include in this term. Our kinetic energy then, on the right-hand side, now we have a translational component and a rotational component. Okay, and those are both written for the center of mass G. Okay, now we need some kinematics relationships to be able to plug things in. Because if we look at this, right, well, we'll go through some geometry. So kinematics and geometry, let's say. We'll go through some geometry to get y1. The others here are known. That applied moment is given. The change in the angle direction we need to determine from geometry. Anything else? Yeah, so the VG we can then relate to omega because this is a rolling wheel. And then we should be able to have it, right? Okay. So let's first go through the geometry of y1 here. Now, this is just a triangle. Okay, we know that it rolled 0.4 meters, which is b. Okay, and y1 is this height where this angle is 15 degrees. So y1 is just 0.4 sine 15 degrees, or 0.1035 meters. So that's y1. Let's see. To get at theta, right? This is kind of nice, right? But this, let's extend my original picture here, right? The amount that, like, maybe it's better to redo exactly what we did here and say, hey, what was pointing down here is now pointing over here this way. Okay, and that is also the theta that we swept through, right? That's the change in our angle. And this is what made contact, right? So this is what was originally in contact here, right? And then this part of the circumference here is exactly B, right? So that's the arc length. So from here to here is B, okay? So down here in our work, we'll say that B equals R theta. Well, in effect, it's negative because theta is in the negative direction there. This is our arc length. Okay, so therefore theta equals minus B over R, which is minus 0.4, 0.2, so minus 2 radians, right? You see our rotation is in the negative direction. Right, the applied torque, it'll rotate this way. Everything's negative. The angle's negative. The omega's negative. The alpha would be negative if it accelerates downward. Yeah. Okay, so our theta's there. Now let's get VG. This is kind of a kinematic relationship, right? Because of a rolling wheel, right? We could look at what VG is compared to the fixed point, or not the fixed point, but the stationary instantaneous point there, and label that. But I think we've done this enough where we know that for a rolling sphere, the motion of the center point, of the center of mass, is just r omega. Okay, this is rolling with no slip. So therefore our omega, because what we want is what is the velocity at the center. So we want VG, so let's express omega in terms of VG, and we'll be able to plug it in. And I think that's everything. If you look up there, I think we now have, back to our energy equation, we have everything written in a way where we should be able to just now plug in and solve for VG. So let's try it, right? Let's go back, plug things in. We have mgy1, those are all known. We have m theta, we now know have values for all of those things. We then have, okay, that equals 1/2 mvg squared, right? That's what we're looking to solve for, so that's fine. Everything else is known. Plus 1/2 of ig. Well, the moment of inertia for a disk is 1/2 mr squared. 1/2 mr squared. And then for omega squared, we'll plug in, well, just for omega, we're going to plug in minus vg over r. So this is minus vg over r quantity squared. And then, re-express this right-hand side in terms of vg. So these both have a 1/2 on the outside. They both have a mass. They both have a vg squared hidden in there. Look at the r squareds cancel, right? Because that's r is inside there. But then what else are we missing? Well, this is just another 1/2 there, right? So then this is just 1 plus 1/2, where the 1 comes from that term and the 1/2 comes from this term. So this is really 3/2. In fact, the whole term here is 3/4. So 3/2, 3/4, 3/4 mvg squared. Okay. So now we're prepared to take this and that and just solve for VG. VG is then just going to be mgy1 plus m theta all over 3/4 of the little m mass square root, because this would otherwise give us VG squared. I'll fully write out all of what we're plugging in here so we're all on the same page about what we're plugging in for quantities, right? This is mass of the disk, gravitational acceleration, 9.81. We determined y1 from geometry above to be 0.1035 meters. Our applied moment, careful here, right? This is why I go to the trouble of plugging everything. Our moment is actually negative, right? This is a negative m. And then also our theta is negative, so 2 degrees in the negative direction. So if you didn't put in, and this is where it's just all that matters is that the work done by the moment is in the direction of motion, so this should be positive in the end. M times theta should be positive, whereas if you just pay attention to the directions of them individually, we would plug it in as a minus 10 Newton meter moment multiplied by a negative 2 radian angle change. Okay, and then on the bottom we have 3/4 of 5 kilograms. And right, and then we just get to the final answer that our velocity of the center of mass is 2.586 meter per second once we plug all those numbers in. Okay, that's it for this one. Okay, so I think this is the last example we'll go over in this video. Again, we have 2 lectures devoted to example problems for these work energy problems. This will be the first one with the torsional spring. In the next video, we'll have another torsional spring system that's maybe slightly more complicated. And then I think, whatever, the most complicated of all of them would be the last one to go over, but even that one's not too bad. Okay. Again, work energy is like kind of a nice tool because it's you know, it kind of simplifies a lot of the analysis that we would have for like the other ones that involve vectors. Okay, let's take a look at this example. Okay, so we've got a mass. Sorry, not a mass. We have a slender bar that's 8 kilograms, you know, 2 meters long, and it's got a torsional spring here down at the bottom, all right? And that exerts a counterclockwise couple. Okay, so we'll represent it on our free body diagram. We'll leave this diagram nice and clean. What we want to know is, so we release it at 5 degrees. It has a mass, right? So we release it there. It provides a moment, okay, that's going to want to swing it back the other way, but it's also got a weight, right? So that all together should give it some sort of you know, restoring moment. At the same time, it's got a weight, and that weight would get more and more. You know, I guess the torque due to that, the moment due to that weight gets more and more as it gets a higher angle. So at some point, the bar will reach an angle of 60 degrees, and we want to know is what's the angular velocity at that time. Okay, so we start with the free body diagram, which I already labeled over here. Let's put in point O here, and we'll just put in well, let's put in, actually on just one diagram, let's see if we can fit in both. So this is our undeformed state, right? The torque, or the moment, the couple, as we call it in the book, the couple or the moment is k times theta. So if theta is 0, that would be the undeformed state. Okay, so then we deform it here at 5 degrees, and I'm even exaggerating that. And then we also have 60 degrees as the 2 different positions. Okay, let's get in here and say here is 5 degrees and here is 60 degrees. Now we're going to actually do a free body diagram for each one of them, but there's the center of mass, there's the center of mass. This is then 1 meter up. I'll just label this bottom one. That one's 1 meter, and you can see what the other one is, right? And then the whole length is the whole length is 2 meters, so that's also 1 meter. All right. Okay, time to put the forces in, right? And actually, let's label these as angles we'll actually put in, so we can keep them as. So this is theta 2, and this is theta 1. Okay, but let's just put the force, since we're only labeling the lengths here for the higher one. Let's also just put the forces on that one, right? So we'll just put the forces on as if this is the free body diagram, and we'll use the other one as a geometry labeling thing, okay? So the forces here, it's always got a weight acting through the center of mass. This now has an applied moment, that is k theta, and then it also has a normal force, n. Okay, and that could be in different directions here, but let's just, I think this bit here. So I guess because it's pinned, it could be in either direction. So let's call this normal in the y direction, and well, we could label it O. We're picking at something here that, or I am here, that's not going to matter in the end, because it's not going to contribute to the moment about the point, about the rotation here. Okay, so then we go to work energy. okay, which is kinetic energy at 1 plus the potential energy at 1 plus the added work here is a kinetic energy at 2 plus the potential energy at 2. And let's see here. We have no motion. We release the thing from rest at 5 degrees. So there's no motion originally. And then we have, this term actually turns out to be 0. Okay? So before we had like this applied moment, k theta in the previous problem, and we entered that here. Well, because this is a torsional spring, we can actually enter it into our potential energy terms. Okay? So this is 0 non-conservative work. And then our spring is in potential energy. So if you're looking for that torsional spring, you'll find it in the potential energy terms. Okay, so let's express all of these terms out, okay? Potential energy in state 1. Okay, it's got, both of these have potential energy. Yeah, we'll just do it. We'll just have datum be down here at the bottom, right? I think that would make sense. And we could definitely choose it at 1, but I think that's going to be, it would be hard to make a triangle out of these two and determine. Might as well just make this datum. And then the y position is how much to go up to their center of masses. Okay, so they're both going to have potential energy, both from the spring and from gravity. So we have mgy1 plus 1/2 k theta 1 squared equals, okay, so this is that guy. Kinetic energy is purely rotational, so 1/2 omega, or I naught omega squared, and that's just pure rotation about a fixed point O, right? Pure rotation about a fixed point O, so we use that version of our kinetic energy. That's right there. And then we have the same term as we had on the potential energy term on the left, mgy2 plus 1/2 k theta 2 squared. And that's that one. Okay, so this is a rotation about fixed point O, and also our moment of inertia about that fixed point. That's the end of a slender rod, and so that is 1/3 ml squared. Let's get into those y positions over here. All right, this y position is going to be, we're looking for y1 when this is 1 meter, right? This is g, and this is O. That's the center of mass, not the full length of the bar. We want to know the vertical position to that. Well, this is just going to be, oh, and 5 degrees is hitting there, right? We've gone inside this triangle. I mean, you could have done it with this triangle right here. Either way, the y1 is going to be the cosine, right? And that should be easy, right? We'll be able to check it here because it's such a small angle. We should get a value very close to 1 meter, 0.9 something. Okay, so you can always check that work. Y2 is going to be very similar. We'll make a triangle here, but now 60 degrees. Here's Y2. This is also 1 meter. This is point G. That's point O. And we get that Y2 equals 1 meter times cosine of 60 degrees. That one I know. That's just going to be a 1/2 meter because cosine of 60 degrees is a 1/2. All right. I think we're ready now. We're looking for the angular velocity in state 2. So that is the omega squared at that time. All right. So well, we can put like a little 2 there. At state 2. Okay, so we can solve for that now. So omega squared state 2 is going to be, let's see, we'll pull the gravitational terms together. mg y1 minus y2, because we have to pull it to the left-hand side, right? We're solving for this, so pull everything to the left and then flip the whole equation around. mg y1 minus y2 plus, put the spring potential energy terms together, 1/2 k theta 1 squared minus theta 2 squared. And that's all the terms. Now we just divide by 1/2 I naught. Well, 1/2 I naught is 1/6 ml squared. Okay. All right. Yeah, I don't mind plugging all these things in. So let's see, just in case there's any surprises along the way. Okay, so this is 8 kilograms. This is 9.81 meter per second squared. This is, well, 1 meter, but cosine of 5 degrees minus cosine of 60 degrees, which is a half. We might as well just put in the 1 meter for all right, so this whole thing is y1 minus y2. Plus 1/2 K is given as 40 Newton meter per radian for the torsional spring. And now this is, okay, I knew we had a reason to do this, right? These thetas are a little bit tricky, right? Theta 1, that is 5 degrees converting to radians divided by 180 degrees times, well, I guess the conversion, maybe we write it like here, right? 5 degrees, and then our conversion is times pi rad over 180 degrees. All right, so you're actually multiplying that out. It'd be 5 divided by 180 times pi. That is squared, right? We need to convert it to radians. Minus 60 degrees, same conversion, pi radians over 180 degrees. That quantity squared. And that's it for the numerator. Divide that by 1/6, 8 kilograms. 2 meters is the total length squared. Square root the whole ugly mess. Plug that in. We get a rotation of, at state 2, of 1.7938 radian per second. All right. So that's it for this, but again, the next lecture, all it is going to be 2 more examples that might be slightly more involved, but not too much, right? This is work energy. This is it tends to be not as involved in terms of working through. There's no vectors on here, right? So, okay.